All right, welcome over to week 13, day 2. Today we are going to continue our discussion of the master method because you all got it wrong last time. So we'll continue talking about it until it is understood. So let's say that we've got a vector. Let's see, int n is equal to read. How big a vector do you want? And so we will make a vector of integers named vec of size n. Okay, so we're going to make a vector of size n, and let's iota it just to fill it with. Or do you want to fill it with random data? Do you guys know how to fill it with random data? You know? How would you fill this this vector with random data? Using a standard library function. Yeah, rand, sure. But how would you rand in a for loop? Yeah, you could. There's also a function called generate that is used for this kind of stuff. You get begin, end, and then you pass in a function to it. I'll never hesitate to teach you guys a little bit of new C++. So I said give me a vector of size 10, and so it gave me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 random numbers. So what's going on here? So this is my read library, right, which just simplifies the input. This makes a vector of size n. It's a vector of integers of size n. This generate function here is going to say from the beginning of the vector to the end of the vector, run this function and put into each spot of the vector the result of this function. Okay. Couldn't you use generate? Yes, I use generate. What is the square bracket, smooth parentheses, things? That is something called a lambda. So a lambda is an anonymous function. It's a function that if I wanted to do the same thing, I could do this int rand 10 return rand. I could have done this. And it would do the same thing. Okay. So what's the difference? Functionally, nothing. This is actually exactly the same code. This and this, exactly the same. It's going to call this function on and it's going to call this function over and over again, and each time it calls a function, it's going to take the return value and put it into the vector. Okay. However, now we have in global space a function called rand10. And so if we have a large project, that name is now taken up. We have a function that returns an int, takes no parameters named rand10, and we can't use it again. And now maybe somebody in the future might want to do the numbers from 1 to 10, right? Instead of from 0 to 9. And that would cause a bug. If you're going to only use a function in one place, then you want to use a lambda. And so a lambda is a function with no name, like this. And it basically does the same thing as passing in a function. Notice there's no parentheses here. I'm not calling rand10 like this. This would actually be calling it. Nope, not doing that. You pass the actual function in, function pointer. So that's a lambda, and they are kind of useful. They're not super useful because you can technically never technically need to use lambda. You can always just make a function and then pass that function in wherever lambda could be used. But if it's a one-off function, you don't need a name for it because it's a waste of a name because you're never going to call it again. So. Okay. Yeah. So we're making a vector of size n. Okay. Now we're going to call our function. Somebody give me a name for a function. Name. Okay. Vector prints. Funky. I like funky better than that. And maybe our function will add up all the elements in the vector, something like that. But it's going to do so. It's going to do so recursive. So if vec dot size is 0, we return 0. So if we don't have any elements in us, return 0. Shouldn't happen, but you know. Let's just say less than 1. Vector dot size equals 1. Then we just return vector dot at 0. Technically, we don't need a bounce check there, but who cares? Okay, so we're going to make two subvectors, the left half and the right half. So this makes a new vector. The syntax, which you might not have seen before, copies a chunk of one vector into the new vector. Okay. And so what we're doing here is we're creating a new vector and we're initializing it with all the elements from vec from halfway through the vector to the end. And then this one is initialized from the beginning to halfway. So beginning to mid, mid to end. And this will pick up the first half, this will pick up the second half, and it'll do so until we hit, you know, size 0 or 1. Okay. Do they still have pumpkin spice lattes? Drinking coffee right now at Starbucks. Yeah. I haven't had my coffee this morning. That's why my brain's running a little slow. It's sitting on the front porch, but I'll get it in a little bit. So vector 1, vector 2. Okay. So then what do I have to do to make this function work? I want to do a recursive addition. How do I do it? What do I return? I want to do this recursively. I'm terrified of for loops. I don't know how they work. So how do I add up this vector recursively? One line missing here. Nope, no while loops either. No while loops, no loops at all. I want to add up all the elements in this vector using the power of recursion. Call the function funky. Okay. Passing in what? Vector 2, vector 1, vector 2, just like that. Are we done? Vector 1 plus vector 2? Like that? Does that compile? No. Nope, that's not doable. You can't add two vectors together. What should we do here? Yes, very good. Okay. Okay. 24 plus 7 is 31, plus 8 is 39. Okay. 10 plus 12 is 22. And of course, there is a standard library function that does this, which is a numeric, I think. From vector.begin to vector.end, and you have to pass it a subtotal to begin with, which is really stupidly annoying. All right. Is that a numeric? It is a numeric. Yes. Okay. DW. Big vector of 5. Okay, so funky and accumulate are generating the same numbers. Good. All right. So probably could have a detour here to talk about testing, but we won't, because our point here is to talk about the master method. So what is the A, the B, and the C for this function? A is the number of times the function calls itself. B equals the fraction, the denominator of how much work each subcall does. C is into the C, how much work is done within this call. So what do we got? Yeah, the only work we're doing here really, well, we got a copy, you know. And so this copy here is actually going to, this is actually most of the work. So this is order 1, right? And so you look at this and be like, all right, that's an order 1, so C is equal to 0, right? Because n to the 0th power is 1. Right? Wrong. This is actually This is order n divided by 2, which is to say order n, right? And then that's order divided by 2, which is to say order n. So what is the work done within this call? N. Yeah. So what is C? Okay. All right, so now we just look at the cheat sheet for this. Okay, so the log base 2 of 2 is 1. So the log base 2 of 2, log base b of a is 1. And we're going to compare this with the C, which is also 1. So what is the running time of this algorithm? We're going to add up all of the elements in this array in what running time? Into the C? Yeah, well, don't. What is C? Don't just write into the C. What is C? Into the login? No. Log base 2 of 2 is 1. 1 is equal to 1. Therefore, the answer is order n login, because C is 1. So this is an n login algorithm. Yep. So this is n, order n log n, way of adding up a vector. You want to find out if it's faster or slower than accumulate. Yeah, it's not into the login, it's into the 1 times login. It's a very important difference there. You'll simulate, yeah, it should be like if you were going to add up a vector, you would do it just as a for loop, right? And it's order n. Our code is slower. And the reason why it's slower is because we are doing all of these unnecessary copies. What we should be doing is just passing in a pair of integers. And the pair of integers are the range, or you can pass in iterators, whatever. So we ought to be passing in just a range and having this thing operate within the range. And when the range gets down to size 0 or 1, we handle those base conditions. Okay. Instead, we're copying this thing over and over again. So, but let's time it. Let's find out. Because who knows, maybe the optimizer will save us. So there is something called chrono, and why does it always do C++.com? So there's something called chrono, and it's kind of annoying because it's so verbose. So should I do this? And the way you do it is you go onto cppreference.com and you copy and paste the code. Let's see, using C. So I don't want to type this over and over and over again. So I'm just gonna, I'll even put this down here, maybe to be a little bit more correct. Okay. So we are going to start the timer by saying HRC : now. That's not a colon, is it? Now. Start the timer, end the timer, and then we're going to do what's called a we're going to difference. It's basically starting a stopwatch and ending a stopwatch. You subtract the two of them, and that tells you how long the funky took to run. And we do so by doing, you just, well, I'll just copy and paste this code here. Right? Stood : chrono : duration. And then you output it by calling .count on it. And then we'll do the same for accumulate. Start is equal to Hillary Rodham Clinton now, and end is equal to Hillary Rodham Clinton now, and diff, and just see out time to run accumulate, and rather than creating the diff, we'll just say end minus now duration double start. No, doesn't like that. There. So funky is 30 times slower with 100,000, and it is 100 times slower with a million. Let's make sure I have the optimizer turned on, otherwise we won't get any useful information. 1 million. Looks like the optimizer was on before. Okay. So yeah, noticeably slower, right? Because of all the excess copies that we're doing over and over again. 100. 10 million. 100 billion. Seven seconds versus 0.03 seconds, so about 200 times slower. HRC, yeah, that's funny. So pretty noticeable difference, right? That's the difference between order and order and log n. Yeah. So now, and we could. We could make it even worse if we wanted to. Let's do some useless calls. Still order 1. Still order 1. Why? Why is this giant line here order 1? What you guys think about that? Because my coffee's sitting on the door. So I'll be right back. Right back. Would the compiler get rid of these extraneous calls? I don't know if it's smart enough to figure that out. Let's find out. Let's see. But the reason why this line here is still order 1 is because we're just counting how much work we're doing at this level. At this level, we're doing 3 adds. And 3 adds is order 1. Okay. So all the work is being done in the subcalls, but at this level, it's order 1. Okay, so that's still 0. So what is the running time of this algorithm now? Assuming the optimizer doesn't see through what my ploy here. What is the running time going to be? What is A? What is B? What is C? Let's try that. A, how many times does the function call itself? What fraction is given to each one of the subcalls? Two. How much work is done at each level? How much work is done at each level of funky? Each individual instance of funky, how much work does it actually do rather than offloading to some other level? C is 1, because still we're doing this really ugly extraneous copy. So now we come back over into here. And what is the log base 2 of 4? 2 to the what power is 4. 2. So what is bigger? Log base B of A or C? C is 1. The log base 2 of 4 is 2. So which one's bigger? The log base B of A. Yeah. So what's the running time of this algorithm? It has changed. And thank you for guessing and being wrong. The only thing I can't deal with is when just nobody answers anything. What's the running time now? Assuming the optimizer isn't going to pull out the extraneous ones. The running time of the program is... Yeah, don't just write into the something like log A. You actually have to do the substitutions for A, B, and C in the answer here. Into the log N? Into the log A? Into the log B base A? You gotta substitute. You gotta tell me what the actual number is. Just n squared, guys. Come on. The log base 2 of 4 is 2. So this is just an order n squared algorithm. I know Yoxtimer said that, but I wanted to see if other people would agree with you or not. So, yeah, don't write order n to the log base 2 of 4. You're just going to confuse people. It's just order n squared. So that's it. So this algorithm now has dropped from... order n squared. And this is why we're practicing the Master Theorem, because it takes a while to get your brain kind of used to it. So this is now order n squared. Run it with a vector of size 1,000,000. It's a little bit slower. I don't think the optimizer saw through us. It's 0.6 seconds before. Now, some people will talk about the energy cost of this. This is kind of a new way of looking at algorithms, is to think about algorithms in terms of the CO2 cost of somewhere in Fremont. My poor server is copying a vector needlessly over and over and over again, and that's burning electricity. And if that electricity comes from a non-green source, then I'm contributing to global warming right now by writing an inefficient algorithm. It's running for a while, huh? Let's try 100,000. Okay, let's try 100, 1,000, 10,000. So it takes 1.5 seconds to process 10,000 now instead of 0.04. 8,000. Problem with cryptocurrency, yeah, a problem with cryptocurrency, other than the fact that nobody can decide why it should be worth anything at all. So, just people, it's how value works. If people decide something is value, it's got value. So yeah, look at this, 50,000, can't even do it. Okay, so let's make it worse. What is A now? If crazy billionaire tweets once, it could lose all value. Okay. Very good. So what's the running time of the algorithm now? This program is still technically correct. That's the really funny thing, is that this will actually give you the right answer. It's doing, no. It's not actually. There. Because I care about correctness. So there, this horrid thing is now correct. Adds vec2, subtracts vec2, adds vec1, subtracts 1. It is in to the third power, yeah. Because A is 8, B is 2, the log base 2 of 8 is 3. 3 is bigger than 1, so it is a order n cubed algorithm. Okay. And just for a morbid sense of curiosity, let's see how long this takes to run with 10,000. Forget about 10,000. 1,000. There we go. 10 seconds to 10 seconds to add up 1,000 numbers. So it is 100,000, about 1 million times slower than accumulate. Yeah. And you'd be like, but why would somebody write a function this way? It's a second. It's a second to add up 500 numbers. Well, let me tell you some stories about when non-computer science people write computer science programs. if you've never studied Big O, then a lot of this stuff is just sort of like a giant question mark. How long does this take to run? So for example, let's say that you wanted to have an array of numbers, and this is actually based on a true story. It's not exactly what it is, I'm simplifying it a little bit, but let's say that you want to have a vector. And actually, let's just make it even easier. So let's say that you have a vector, and you're going to be constantly reading in numbers from the network, and you want the vector always to be sorted. So you want, let's say, the biggest number in front, smallest number in the back. Every time a new packet comes in with a number, you put it into the vector wherever it should be. And then periodically you will take the leading element off the vector. What's the running time of that algorithm? Just let's say for reading. Let me sketch it out for you. This isn't recursion, it's not master method. I'm just going to sketch it out there. So void add to vec, passing in a vector of integers named vec by reference, and a new integer to add. Vec is a sorted vector. X is the element to add to it. What is the running time? Well, I can tell you how they did it, which was this: vector.pushback X, right? And then sort except it wasn't actually this nice, because they weren't using the standard library. They did their own thing. But for the sake of argument, we'll just say this is their algorithm. So what is the running time to insert one element? What is the running time to insert one element? Constant to insert one element. Order n. Isn't sort n log n? It sure is. So pushback is order 1. Sort is order n log n. Or it could be worse if you wrote your own sorting function, which this is a while ago, but maybe they did, and maybe they used bubble sort. One is constant running time, yeah. So what is the running time to add one element to this vector? They weren't using sort. I could probably pull up my source code for what they actually did, but this makes for an amusing anecdote. So what is the running time of add to vec? Vec comes in sorted, vec leaves sorted, X has been added to it. Yeah. So the running time to insert one element is, in fact, order n squared. What is the running time to insert n elements? in times, you're going to do n squared work. What is the running time? What is n times n squared? No, it's not exponential. It's n times n squared, right? N times, you're going to insert, you're going to call this function n times. And so n times n squared is n cubed. Okay. So, is there a faster way of doing this? Yes. For one thing, you know, you can call quicksort or whatever this is, right? So, by using a faster sort, what's the running time? What's the running time if they used the standard library instead of writing their own? We're inserting n elements still. So what is the running time to insert n elements? It's n times n log n. So it is in fact order n squared log n. Is there a faster way of doing this? Is there a faster way of doing this? Yes. Now, you know, you might say, well, just do all of the pushbacks and then sort it once at the end. But they had a requirement that the thing always be sorted. Okay. And since this was kind of in real time reading from the network or maybe from a file, it was basically had some things that had a higher priority than other things. It's kind of what was going on behind the scenes. I mean, you can use a different data structure that auto sorts. Yes, you can. And so by using a priority queue, which is a queue that sorts things by their priority, it's always sorted all the time, then the running time dips. The running time drops to n log n, right? And so with just a little bit of like computer science savvy and know-how, I was able to reduce the running time of this algorithm, which again, I'm sort of brushing over a lot of the details that don't matter, but I was able to reduce the running time from order n cubed to order n log n. And I think that my first crack at it actually reduced it to order n, and then that got rejected because it didn't meet the requirements that they didn't tell me. And so basically I started working for this group, and they gave me their code, and they're like, make it work better. It's really slow right now. I don't know why. And so I just went home, spent a week. I didn't contact them for a week, which was my bad. I know better now. You should always be in contact, especially when you're starting a new job. But at the time, I was just like, nah, I can redo this. You know, it took me a couple days to read over all their code and kind of like understand what's happening. And then I rewrote. I identified areas where I'm like, ooh, you shouldn't be doing that. You know, and drastically sped up the code because they were just like, well, look, it's, you know, it was sorted before, it's sorted after. What's the problem? You know. And in fact, if they had used bubble sort here, bubble sort would actually be able to do an order n time, which would still be slower, but not that slow, you know. And so, you know, I don't even remember. They were probably using like selection sort or something that just had no benefits. But if you're gonna use if you're going to insert a single element into a sorted array, bubble sort can actually do so in order n time. And so if they were using like selection sort, then it doesn't matter. It's always in squared. And yeah, anyhow, so I kind of went over it and went over it and went over it. It's kind of like the merge sort golf assignment, except instead of trying to minimize semicolons, I was like, yeah, this is slow. It's unnecessarily slow, and it had bugs in it. If you fed an array of all zeros, it would crash because it did averaging. So it would add up all the numbers and average them, divide by. No, at some point it would divide by the sum total of the vector, and so if you fed in all black, all zeros to it, it would segfault. It would throw an exception or whatever, floating point exception. So anyhow, so the point is that with a little bit of this understanding of big O stuff, you can sometimes drastically speed up your code, and you'd be like, well, why would anybody write code this stupid? And my answer is, you would be surprised. You'd be surprised in the real world that there are order n cubed algorithms out there that should be way, way faster. Like n log n is far faster than this. Okay. So let's do a couple more examples of master method, and then I'll introduce you to your programming assignment. So. Okay. What is A? What is B? What is C? A. How many times does the function call itself? B. What is the fraction, the denominator of work being passed on to each subcall? And C. How much work is being done on each level? A is equal to 2. Yes. It is 2 because we're calling ourselves twice. Are you guys starting to see the pattern here? And here's the thing, right? Like, when am I going to use this? Well, anytime you have a recursive call, it's a really good idea to know what the big O running time of it is. Because, that's a big part of computer science is understanding big O. And so anytime you have a recursive function, if you know the master method, the Master Theorem, then it doesn't work on all recursive algorithms. There's extensions to it that work on more. But, like, for example, it doesn't do exponential running time things like Towers of Hanoi. Because it's not a division. Like, most recursive algorithms, you divide by 2, right? For Towers of Hanoi, you subtract 1. And so that doesn't actually work. When B is 1, if you do the math, like, the thing explodes. It doesn't work with it. So can we do an in-depth lecture on big O? I mean, this is your in-depth lecture on big O. Yeah. So, yeah. But once you start understanding the Master Theorem, you just like, all right, how many times do I call myself? Twice. What's the fraction of work being passed to each subcall? 3. It's the denominator. It's that number right there. And how much work is being done? N to the cth power, C is 1. Order n. Okay? So if we click back over here to the slideshow, what is bigger? 1 or the log base 2 of 3? The first time I really understood big O, it took a year, but better late than never. Yeah, it takes a while. It takes a while to get it. And it's like the really deceptive thing is that your code works. Like, his code worked fine if you're passing in 50 numbers. You can have an order n cubed algorithm, and you run it, and it's like, boop, you're done. And you can verify your code is correct and everything. It's just once it started running on 1,000, 10,000, whatever, it's like there's a bug in here somewhere. I'm like, no, it's not a bug. It's just slow. It's just really unnecessarily slow. So what is the log base 2 of 3? It's going to be in between log base 2 of 2 and log base 2 of 4, right? Because it's log base 2 of 3. Larger numbers will help you to see that it needs to be faster. Yeah. Whenever you run your code, you should test it on small numbers just to make sure it's correct. So log base 2 of 2, log base 2 of 3, log base 2 of 4. Right? This is 1. This is 2. So the log base 2 of 3 is somewhere going to be between 1 and 2. So it's actually bigger than C. Still. Okay. Got 0.63. No, it's 1.6. Okay. So you see how you can just like eyeball these things? So 2 to the what power is 2, 1. 2 to the what power is 4, 2. So because we know 3 is between 2 and 4, we know that the algorithm, or the logarithm, is going to be between 1 and 2. And you can calculate it out if you want. Or you can just say this is an order n to the log base 2 of 3 time. That's fine too. Or order into the 1.6. Either way. Either way works. I did it backwards? You're absolutely right. I did. So there's only one solution to that. Change the code. That way I'm not wrong. So the running time of this code is log base 2 of 3, or order into the 1.6. But you're absolutely right. You're absolutely right. It was log base 3 of 2. And that is, what did you figure it out as, 0.63? Okay. In that case, it is less than, right? And then it is going to just be order in. Okay. It's nice being the professor. If you make a mistake on a program, you generate test cases that are wrong. Students just have to follow your bug. It's great. It's fantastic. Okay, so, but what we had here before, like this. So for this one, A is 2, B is 3, C is 1. So the log base 3 of 2 is less than 1, so it's order. Right, because it's less than C, the answer is into the C power. Okay, let's do one more because I sort of screwed that one up, didn't I? All right. Okay, what's the running time of this? let's say that this is the dude's code who's doing selection sort for like an order n squared sort. Quick refresher on how we determine C again. C is the exponent of the amount of work we're doing. So at every level, we do n to the cth power work. If it's constant running time, C is 0. Right? If it's constant running time, if we didn't have our copies here, then C would be 0, because n to the 0th power is 1, which is constant running time. This is order n, which is n to the 1st power. C, again, is the power of the work you're doing. So in that case, it is 1, if this was our biggest thing. But we're doing selection sort. So what is C? Yeah. C is the exponent. Okay. How many times are we calling ourselves? What is A? What is B? What is C? What is A? What is B? What is C? A is indeed 1. By the way, this thing got me through grad school. There was a lot of algorithmic analysis in grad school. And once I really understood the Master Theorem, it just sort of internalized it. I was just like, oh, that's that's an order n squared algorithm, And basically I leaned on this like for a long time. So you're maybe going to be okay forgetting this for now, but I highly encourage all of you to go to grad school, by the way. It's, by the time you finish your bachelor's degree, you're going to have a certain basic level of competence across computer science. But if you spend another year in school, which is usually all that master's degrees take, I personally spent more time there because I just enjoyed being in school. So I ended up taking kind of like all the classes that interested me. By the time you finish your master's degree, you've taken all of the core classes again. So you sort of take things like data structures at the freshman level, and then you take data structures again as a junior, and then I took data structures again in grad school. And each time you take it, you kind of learn more and get kind of a deeper understanding of things. And so I feel like a master's degree is really, really, really beneficial. It's another year of your life, but you just kind of understand all of computer science at a deeper level. So highly recommend it. Plus, nobody in the department paid to go to grad school, which is something that a lot of people don't really understand, is that it's usually free. Not always. Depends on the program. It's the kind of thing you should check first. You ask, what percentage of your grad students get support? Get financial support, get fee waivers, get tuition waivers. And at our department, basically anybody who wanted a fee waiver, a tuition waiver, would get one. Which meant nobody paid tuition unless you wanted to. And some did. Like, if their work was paying for their tuition, sure. Sure. They would pay it. Because in order to get a tuition waiver, you have to TA. Right? You have to teach or do research, one or the other. So our department had so much money that there was basically like, you want to TA a class? TA a class. And we could always use more people helping out teaching because we had a lot of people in the program. And so grad students make the world go round. And so basically, you'd be like, yeah, I want to help teach CSci 40, whatever, and then you don't pay tuition that quarter. It's pretty simple. All right. And then you get paid a little bit of money on top of it. Like when I was in grad school, I didn't pay any tuition. And I was given $19,000 a year, working essentially part-time or full-time. It depends on your perspective. Can't grading or not. And that was enough to live on. Like $19,000 a year, I had a roommate or two and a car, and yeah, it was enough to get by. But okay, so B here is 2. Because this is half and this is a quarter. So it's going to decay much slower on this side of things, right? Like think about this. Like, suppose we didn't do the first half at all. Then how many levels deep are you going to do? You go divide by 2, divide by 2, divide by 2, divide by 2, divide by 2. When you divide by 4, it hits the base case much quicker, right? So you hit the base case really quickly this way, and then the other way, it's divide by 2, divide by 2, divide by 2, divide by 2, divide by 2. So it's whichever one's bigger, right? So in this case, B is 2. A is 1. The log base 2 of 1 is 0. So this C is 2. So in this case, A is 1, B is 2. The log base 2 of 1 is 0, because 2 to the 0th power equals 1. C is 2. And so we look down here, we see 0 is less than 2, so this is an order in squared algorithm. Okay. So yeah, now it depends on the college. Not all colleges have money to pay for the tuition waivers. So you want to check that first before you go to grad school. But at UC San Diego, we had so much money, it was kind of ridiculous. Okay. And then if we were to change this to just regular sort, what's the running time of the algorithm now? You just got a UC San Diego pamphlet, yeah. It's harder to get in now. And so that's, despite the fact they've expanded enrollment, like just more people are trying to go there now. So it's kind of annoying. Like Nick Moya, who's a really smart dude, you know, high GPA, TA, did all this stuff, got the, you know, he got waitlisted for UC San Diego. So kind of annoying. All right, what's the running time of the algorithm now? What is C? What's the exponent on that? He's at Irvine now, yeah. Mm-hmm. Well, what is C? What is a log? What is a diorama? Yeah, it's not. This doesn't map into our. This doesn't map into our equation very well. But I will tell you that you can kind of eyeball this and be like, all right, the A log B stuff is going to be low, and so this is going to be the dominant thing. The dominant thing is we're sorting the vector at every level. And so that's going to turn our output into an order in log n algorithm, because we're doing way more work per level than we are splitting the thing. What about now? What's the running time of the algorithm now? Order log n. That is correct. This is now an order log n algorithm. Very good. And so something that would be order log n would be like a binary search. You can recursively do binary search where you call search on a vector and you a sorted vector, and you look at the mid element. If the mid element matches, return true. If not, recursively call on the half of the array that has the number in it. So if you pass in the numbers from 1 to 20, you search for 10, or you search for, let's say, 5. If you search for 10, you hit the midpoint, return true. But let's say you search 5. You check the midpoint, 10, okay, it's got to be on this side. So you essentially throw away half the array, and you search over there. Okay, found it, return true. What if you're searching for 1? Okay, it's to the left. Okay, it's to the left, it's to the left. You throw away half the array every time. So you'll hit the bottom, you'll hit the ground floor, you'll hit the base case in a maximum number of login steps. And how much work is done at each level? 1. Just a single comparison. And so that would be a case like this, where you make 1 recursive subcall. You don't even have that going on, really. You just, at every level, you don't even have, you're not even going to do a copy, really. It's going to look, well, yeah, you'd have to pass in iterators, but yeah, basically B is going to be 2, A is going to be 1. So for binary search, do you guys understand binary search? Like 1, 3, 7, 11, 17, 20. If you search for like 3, you come into the midpoint here. And whichever way it is, then you hop halfway in that direction. And so the fraction is 2. The amount of work you do at each level, you do 1 recursive subcall. You recursively subcall binary search to the left or binary search to the right. It's 1 recursive subcall. The fraction you work over is either the left half or the right half, so the denominator is 2. The amount of work you do at each level is 1. So the log base 2 of 1 equals 0. Sorry, C is 0 because it's into the 0th power, which is 1. And so C is equal to 0. It's this case here. So the answer is order log n. Yep. Makes sense? So it's n to the 0th power log n, because 0 equals 0. We're essentially doing 0 work. You know, it's a single comparison. It's n to the 0th power. Don't forget that. And 2 to the log base 2 of 1 is 0. So it is a logarithmic algorithm to do binary search. Okay, so that's enough on. Let's do one more. Let's do one more. Just to see if you guys get this. Well, depends how quickly you guys can get it. What's running time of this algorithm? What's A, what's B, what's C? First. A is indeed 4. Mm-hmm. What is B? B is 4. Okay. So the log base 4 of 4 is 1. 4 to the first power is 4. So log base 4 of 4 is 1. C is 1 also. So this is, in fact, an order n log n algorithm. Because the log base 4 of 4 is 1. C is 1. The two of them match. So it is an order n log n algorithm. What about now? A is still 4, B is now 2. Very good, Aaron. It is, in fact, an order n squared algorithm now. What about now? Make the math easy. Make the math easier on you. What about now? A is 4. B is 16. C is still 1. It's not into the quarter. It's not into the fourth. Think about it. There's a bit of a balance between the fraction of work you're passing on and the number of times you call yourself. With merge sort, you're passing on half the fraction twice. So they kind of balance, right? In this case, we're passing on a 16th, a tiny little sliver of it, 4 times. So we're essentially losing 3/4 of the array every level we go down. So it's actually going to be much faster than if you cover the whole thing. Not into the 8th. So, resume slideshow. Discard the annotations. So in this case, the fraction we're passing on is 1/16. We're calling ourselves 4 times. So the log base 16 of 4 is 16 to what power is 4? N to the 8th power is incredibly slow. Yeah, it's not the slowest in the world, but order n to the 8th is like really kind of bad algorithm. So what is x? Half, right? Because the square root of 16 is 4. So 16 to the 0.5 power is 4. 0.5. And so, what's bigger? Log base b of a or c? C is bigger. So what's the running time of the algorithm? Order in. Okay. I think you guys got it now. Yeah, you don't have to write into the C when C is 1. Just write order in. Okay, so that is the Master Theorem. That'll be what your quiz is on. And there'll probably be on the competence exam as well, just to make sure you guys got it. In the meantime, we are going to do a coding competition. So the coding competition is here, sudo deploy homework, seaside 26, TDD competition. And if you are not present for my class, sucks to be you. You should have been here. But all of you students that are here, thank you for being here. You are rewarded by getting to do a programming assignment. Yay! How was it n squared before then? If C was like 2, then it'd be... basically, the issue is what dominates. Either log base b of a dominates, in which case it's going to be order n to the log base b of a, or C dominates. Like if you do a ton of work at each level, the fact that you're doing a ton of work at each level will dominate the number of recursive subcalls. And so if you're doing like an n squared work, like the selection sort at every level, then that will dominate and it'll be an order n squared algorithm. And if it balances, then it turns into order n log into the C log n. So if the fraction balances the work done at each level, like with merge sort, then it turns into like an in login or an into the cth power login. Okay. Yeah, if C is 1, then it is order in, because it's into the cth power. Okay, so TD, you can have a partner. We'll just do it alphabetically. Aaron and Charles, Connor and Geraldo, Gregorian and Harry, Joshua and Yoxlamer, Sarah and Tomas. Okay, so we have 2, 4, 6, 8, 10 students online right now out of the 24 still in the class. So thank you to the 10 showing up. You get to do a coding competition for extra credit and stuff. So make sure that you put on your main.cc who your partner is, because the cheat checker will flag your code for being similar to theirs. So just on the top of the file, just say, my partner is Aaron or whatever. Okay. So for this assignment, you're going to be learning about TDD. TDD is, let me show you what this thing looks like. Clean. Please enter your name, Bill Kearney. And so the first thing is to verify a name. A name should be 2 words, and the first letter of each name has to be capitalized. And there's some other rules you'll see in the README file. So that's the first thing you have to do. It should be pretty easy. And then for this one, this is elevation data. It's kind of like bridges, mountains. And so like if you pass in this location here, then you travel downhill in the direction that is of steepest descent, I believe. So it'd move from here to here, and then it'd move from here to here. And then that's a valley. You see it's surrounded by bigger numbers, and then it would stop. So this is going to be, what is this? 1, 2, 3, 4, 5, 6. Row 6, column, 5 probably. Count 0, 0, 1, 2, 3, 4, 5, 6. And so it'll tell you ski to this location. Maybe it's the other way down. 6 and 5. I don't know. Does it start at 0? Does it start at 1? Okay, so at 0, 0, you ski to 0, 1. You ski downhill. So row 0, column 1. Okay. Okay. And so when you run the assignment, you can type test, and it will run the gtest suite. And you have to create tests for each one of these functions. And the tests look something like this. So basically, you make a test suite like this, and you call the function. The function name is accept name. You pass in the input, and you say what the output should be. And so what the test suite does is it runs each of these function calls. It runs this, it runs this, it runs this, it runs this, and compares the output with the result that it should have. And so I've got a big set. These are all my incorrect tests. These are bad names. So I've got a bad name list. I've got a good name list. And basically your job is to generate tons and tons of test cases and very thoroughly make sure you pass an empty string, stuff like that, right? Think about all the different ways that things can go wrong. Like the first letter has to be caps. Is a number caps? No, it's not. That's false. What if your last, what if it ends in a caps? False, right? So, little 2 chains. Yeah, it's a famous rapper. Okay, what's the time limit to do this? If you can complete this within an hour, you will get even more extra credit. If not, you have until Tuesday to do this. Okay? So, begin. Let the games begin. If you're watching at home, you have to do this too. Do on Tuesday. So, but you're not going to be able to get the extra credit because you didn't show up to class. So.